Hello, everyone. My name is Joshua Zhao, and I'll be presenting the paper, The Resource Problem of Using Linear Layer Leakage Attack in Federated Learning. This work is a collaboration between Purdue University and University of Southern California. In this work, we explore federated learning privacy. Particularly, we look at linear layer leakage, which is a data reconstruction attack aimed to directly and analytically recover the client data through the gradients of an inserted, fully connected layer. While this method is powerful, scalability poses a problem. While linear layer leakage attacks are able to scale to secure aggregation and FedSGD, this comes at a large cost of using extremely large, fully connected layers in order to maintain a high leakage rate. In this work, we show that the resource cost ends up coming from an incorrect perspective of how to attack aggregate updates. By utilizing sparsity in the attack, we can decrease the model overhead size by over 300 times and the computation time by 3 times for a 1,000 client attack. Here's an overview of the presentation. Federated learning is a decentralized learning method originally aimed at allowing training without violating user privacy. With a growing amount of data and also growing privacy concerns, federated learning has become very popular. In general, a training round will consist of a server sending a global model to participating clients, clients training the model on their local data and sending their local update to the server, and in some cases encrypted, such as insecure aggregation. And from here, the server aggregating the received updates and updating their global model. However, while this premise of sending gradients instead of training data to a centralized server is promising at first, many prior works have shown that user data can still be leaked through the update themselves. This was shown in optimization-based reconstruction attacks and also through linear layer leakage. Linear layer leakage is based on the idea that the inputs to a linear or fully connected layer are stored in the gradients. So if the linear layer is placed at the start of the model, or if the input is pushed to where the linear layer starts, a malicious attacker can then directly reconstruct the client trained data. And this can be done through a simple division, really just the weight divided by the bias for the activated neuron. However, this does require one thing, which is for a single input image to activate each neuron. If multiple images end up activating the same neuron, the reconstructions will fail. And this is shown in the figure at the bottom, where the first image, the dog, is reconstructed correctly because only a single image activated the neuron. However, the bottom two images, the car and the fish, they end up activating the same neuron. As a result, the reconstruction fails, and the reconstruction is more of a combination of the two images. So Robbing the Fed really built on this idea and proposed a more efficient linear layer leakage approach, and efficient in the sense that it achieves a higher leakage rate for a smaller fully connected layer size. Furthermore, it achieves better scalability to larger batch sizes and also to secure aggregation. However, this scalability really comes at a cost. Federated learning with secure aggregation ensures that a server can only see the aggregate update. In this case, while linear layer leakage attacks like robbing the Fed can still attack secure aggregation and maintain a high leakage rate, this requires scaling up the size of the linear layer. Ultimately, this becomes very large. As an example, for tiny ImageNet and a batch size of 64, robbing the Fed gets about a 77-78% leakage rate with 256 units in the fully connected layer. Now, with 100 clients and a total of 6,400 images, the fully connected layer size needs to increase accordingly. So to achieve the same leakage rate, we would need 100 times the number of units. This would be 25,600 total units required. And this is extremely large, which is something like a 2.3 gigabyte model oversized head, just from the attack itself. We now bring up Mandrake, which is another linear layer leakage attack aimed towards scalability for secure aggregation. Now, compared to robbing the Fed, this method splits the scaling between the number of clients and the batch size. And as more clients are added, the number of convolutional kernels increases. And if the batch size increases, the fully connected layers increases. With this design, the weight parameters of the fully connected layer used for leakage are split between clients. In a sense, only the weight parameters connecting to the convolutional kernels for each client are used for the leakage itself. And building up on this, we now bring up the idea of sparsity for linear layer leakage attacks. Ultimately, for linear layer leakage attacks, the number of weight parameters must be at least the number of total pixels in all images. And oftentimes, it'll actually have to be more because the leakage isn't perfect. However, as the number of clients increases, this number will also increase multiplicatively. So for instance, if we need 4 times the number of neurons just to get normal baseline leakage, then we also multiply this total number by the number of clients to achieve the same leakage. However, this increase really comes from an incorrect prior perspective of treating the aggregate updates as a super batch, which leads to very large model sizes. Instead, the key idea we propose is that even for an aggregate update, clients still only need to have enough parameters to store their own images, and all other parameters can still be zero. This ends up leading to very heavily sparse models and further allows sparse tensors to be used to decrease the model size, and also the sparse tensor operations will reduce the computation time. As seen on the figure on the right, Mandrake fundamentally can be used following this idea. Particularly, only the weight parameters connecting to each slice of convolutional kernels for each client need to be non-zero. And since the weight parameters are the large majority of parameters in this attack, this large majority ends up being zero. So very sparse models. So now we show some experimental results. This is for tiny ImageNet, which is downscaled to 32 by 32 by 3, and for the table on the right is for 1,000 clients. The figure on the left shows the model size for different number of clients. In the case of robbing the Fed, it increases to nearly over 6,000 megabytes for 1,000 clients. And in the case of the sparse attack, for one client, it's only 18 megabytes, and for 1,000 clients, it's only 18.3 megabytes, so a very, very small decrease. The table on the right just shows the model size overhead for 1,000 clients relative to different vision models, so MobileNet being relatively small and VGG being a rather large model. So here we also see the model size overhead for different data sets under 100 and 1,000 clients. And a very similar trend is seen here. The sparse weights really can decrease the model size overhead compared to the robbing the Fed. The figure on the right now shows the computation time for these. For the sparse weights attack with 1,000 clients, it adds about a 6.5 second overhead. However, for robbing the Fed, for the same leakage rate, it needs to add a 21.9 second overhead. This is about a 3.3 times decrease in overhead for the sparse attack. And finally, the table on the bottom shows the sparse Mandrake attack and the robbing the Fed leakage rate. Even with a significantly smaller model and significantly reduced computation time, sparse Mandrake is still able to achieve equal or almost equal leakage rate compared to robbing the Fed. So really, sparsity does not bring any downsides here. Thank you.